In this video, we will be talking about wave properties. After watching this video, you should be able to define what a wave is, distinguish between a longitudinal and transverse wave, and understand the anatomy or makeup of a wave, so the different parts and what's going on in a wave. So let's get right into it. There's two types of waves that we're going to talk about in this class. The first is called an electromagnetic wave, and the second is called a mechanical wave. And basically, the big defining factor that determines whether or not you have an electromagnetic wave or a mechanical wave is whether or not it's able to transfer energy through a vacuum, which would be something like outer space, or if the energy needs to be transferred through a medium, which would be something like water or air. Okay, so an electromagnetic wave is able to transfer its energy through a vacuum, which is really good because, as we know, light from the sun transfers from the sun through outer space to Earth, and it reaches us here. If that energy was not able to actually be transferred through a vacuum, we'd never get sunlight from the sun, and basically life on Earth would not exist. A mechanical wave, on the other hand, is not able to transfer energy through a vacuum. It must have a medium. So for instance, if I go into outer space and I were to start talking to you guys, you'd see my mouth moving because that's light reflecting off my face, but you wouldn't hear anything because sound is a mechanical wave. It needs a medium to transfer through, and so in this case it's air. All right, so we'll take a look at this a little bit further. Right now I'm going to just kind of talk about the basics of a wave, and we're going to talk about the difference between a wave train, a pulse, and the different parts of a wave. So let me just get to a color that looks good. Let's go with green. All right, so the first thing is, let's say I have a rope, all right, and so here's my rope, okay? And let's say I take my hand down here on the end, so I'll draw a hand here, and I make my hand go up and down once, okay? So what happens to the rope? Well, you would get something called a pulse formed in the rope, okay, and it would be moving in this direction, okay. This is called a pulse, which is just one disturbance in the rope, okay. Now, let's say I were to do that same thing. Let's say I were to take my hand and I were to continually move it up and down over and over again. Okay, so it's moving up and down over and over again. What would happen to the rope? Well, the rope would start to do something like this, where it would make what's called a wave train. I'll try my best to make this as even as possible, but my drawing abilities are not that great. So this is called a wave train. Okay, so a pulse is just one, and a wave train is, you know, multiple pulses really. And if we can kind of, let me change colors here, draw a line going through the middle of this wave train, which I'll try my best to draw it as even as possible. Again, this won't be perfect. I'll have a different slide where it kind of shows us a little better. We need to start talking about the different parts of this wave. So the first thing I want to talk about is there is this piece here from this yellow line to the top here. That is called the amplitude. The amplitude, which typically is represented by an A. Okay, so that's the amplitude. And that is the height, or in terms of the wave, the intensity. Okay, so if you have a really strong wave, you'll have a much higher intensity. Also, this top point right here, the very peak of this guy is called the crest. The crest. Whereas the opposite of the crest is this point down here. This is called the trough. Okay, so crest is the top part of the wave, the trough is the bottom part of the wave, the amplitude is the height from this, we'll call it the equilibrium position, to the top of either a crest or the trough. Okay, so that's the amplitude. We could draw a line here and call this A also if we wanted to. Okay, now one wave is starting from here, getting back to the same point, which would be here. Okay, that's called one wavelength, all right? And we'll talk a little later what that's usually represented by, but it's called this symbol called lambda, and if you want to know it in English, it would be spelled like this, L-A-M-D-A. lambda, which is lambda, which is one wavelength. So I'll write that in here. Equals one wavelength. Okay, so one wavelength is going from here to there. And one piece we want to talk about is being in phase and out of phase. And so I need to draw another wave here. Let me get a different color. Let's see here. Gray looks good. If I draw, I apologize, we can even use the same wave. Let's just use the same wave. This point right here is in phase with this point right here. They are, if you look at it in terms of degrees, they are 360 degrees in phase with one another. Whereas this point right here, compared to, say, this point down here, this is out of phase. And this will make more sense a little bit later on when we start talking about constructive and destructive interference. But for right now, just keep in mind that the points, if they're the same, that's called in phase, and if they are opposite of one another, they are out of phase. Okay, and so out of phase, this was 360 degrees. What's half of 360 degrees? This would be 180 degrees. And if you guys are familiar with the circle in trigonometry, this is 2 pi in radians, and this would just be pi. Okay, so let's move along. So here's maybe a little better picture of a wave train going on here. Waves, they do only transfer energy. Okay, that is going to be a big key to keep in mind. All right, I will ask questions about that over and over again. Are waves able to transfer like matter? And the answer is no. I mean, if this is a rope here, and I swing this rope up and down, up and down, up and down, do you get a big pile of rope at the end here? The answer is no, right? The rope doesn't transfer itself down, but you do get energy transferred through that rope. Okay, and as I said in the previous slide, pulses are single disturbances, so like we could kind of consider this as one pulse here. And then a wave train is multiple pulses together. Okay. Questions that I could ask you guys would be something like, as the wave moves, what happens to point A? Okay. And something to kind of just keep in mind is that this wave is moving from left to right. Okay, so the velocity would be going from left to right. So here's point A. What ends up happening to point A as this wave train moves along? What direction does it move? And if you kind of just, it's kind of, for me anyway, it's a little difficult to imagine, but if you can imagine as time passes, what direction is point A going to go? It's going to move down. And the reason why is because as this portion of the wave goes through A, it's going to cause it to go down. Okay, so point A would move down. What about point B? Well, point B is right here. As the wave continues to propagate this direction, what is point B going to do? It's going to go up. Okay, point B would move up. And then point C, as the wave again moves this direction, what is it going to do? Well, the next portion of the wave is going to make it go down. Okay, so those are types of things I could ask you, is like, what direction would a point move on this wave train? And notice, never once did I say, well, it moved right or left, okay? Because, again, this wave is propagating perpendicular to its direction of movement, so you got to keep that in mind. So there's 2 types of waves that I mentioned earlier on. There's something called a longitudinal wave, and there's with those, basically what it happens is the direction of vibration is parallel to propagation. And that sounds real fancy, but if you kind of take a look at this graphic down here on the bottom, basically here you've got a wave pulse going through this medium, whatever this is. It looks like Lego blocks all mixed together. And you can see the wave pulse, there it is moving through, right? And it's going through. Basically, the direction of its movement is parallel to its propagation. So the wave kind of goes like this as it moves through, okay? Which will be just the opposite of the next type of wave, okay? So let's take a look at, say, a speaker, because sound is a longitudinal wave. If I have a speaker here, let's say this is my speaker. Okay, how a speaker actually works is, well, first let me draw some air particles. Okay, let's draw some air particles here. How a speaker actually works is, as the speaker makes noise, or it creates a sound wave, so make a sound wave here, As it makes a sound wave, the particles either compress in a point, so let's make some more particles here, get some compression going on, and then you have a point where there isn't much compression, which is called a refraction, and then you have a compression over here, so make a lot of dots there. Okay, and so these points here and here, those are compressions, and then this part in the middle here is called a rarefaction, which I realize I can't draw very well, so I put it down here in the bottom. If I put my speaker here, okay, and that's my speaker again, and it starts making noises, basically the air particles get clumped up where there's a high density of particles called a compression, and then there's an area of low density, which is a refraction. And then again, a wavelength, which we just have barely touched on, is going from one compression to another, or one refraction to another is also a wavelength. Okay, either one is fine. So here is like just a tuning fork doing the same kind of thing here, where again, here is a compression, and there's that compression moving through, continuing to move along through the air, okay? And then here is a rarefaction here, again, just moving along through the air. Now the second type of wave is called a transverse wave, and the direction of vibration is perpendicular to the direction of propagation or its movement. If you want to look at propagation like movement, that's just fine with me. Okay, so here basically a pulse is moving this direction, and you'll notice the particles go up and down relative to the direction of the wave movement. Okay, so you can see it go up and down, and even though the wave is moving perpendicular to that direction. All right. An example of a transverse wave will be stuff like light, or radio waves, or microwaves, or any type of electromagnetic wave is a transverse wave. And so again, a slinky is real good at showing actually both types of waves in terms of longitudinal and transverse. If you take a slinky and you, let's say you push it this way, like you actually squeeze it, you're going to create a longitudinal wave, because what ends up longitudinal, I may be spelling that wrong, I apologize. You're going to squish it up at one point, and that squished up piece is going to kind of move through the slinky, and I'm not a good drawer, but you're going to have points where there are compressions, and you're going to have points where there are rarefactions. And we'll do a lab with this with slinkies, so you'll be able to see this happen. You also could take a slinky, and let's say your hand's here, and you make your hand go up and down, right? The slinky will go like this. Even though the wave is moving this direction, the particle movement is up and down, okay? And that's called a transverse wave. All right, so two different types of waves that you should be familiar with. So here are some definitions of waves, and I've talked about some of these things, but just so you have it in writing, or like I guess in normal text, not my handwriting, of wavelength, which is represented by this symbol called lambda, and again that's Lambda, and that's the distance for one complete vibration or one complete wavelength. Okay, so down here on the bottom you can see from crest to crest is one wavelength, and you actually could say from trough to trough is also one wavelength. I mean, either one's fine. Or you can even pick this spot here, from here to there, that's also one wavelength. It doesn't really matter where you choose to go on the wave, it's just as long as it's one full cycle has been completed. The amplitude is usually represented by A, and it's related to the energy of the wave. So like I said, if this guy gets really high, that's a really high amplitude, and so it has more energy. Okay? The crest is the high point of the wave, the trough is the low point of a wave. All right, so you should be able to identify those characteristics of a wave. So let's do a little bit of practice here. I have 4 waves going through this picture, and I'm wondering which wave has the largest wavelength. Okay, largest wavelength. So looking for the longest wavelength here, and if you look at all these guys, B is looking pretty long, because basically B takes up this whole thing. That's one wavelength right there. You only see one wavelength on the screen right now. So B would have the largest wavelength, which has the highest frequency. Now we haven't talked about this that much yet, but frequency is basically the rate at which the wavelengths pass by a point. Okay, so if we look here, who has the most, or I guess really another way to look at it is who has the shortest wavelength. Okay, and so if I look for who has the shortest wavelength, it's sure looking like D is pretty short. I mean, D is one wavelength right there, and no other wave is that short. So D would have the highest frequency because you have a bunch of wavelengths on this one picture, whereas B only has one wavelength. Which wave has the highest amplitude? So which one gets the highest, crest and trough? Well, it'd be A, right? A gets really high up there, and then there's A again there, and then there's A again there. So it'd be A would have the highest amplitude. And which waves have the same wavelength? This one takes some looking. I actually had to stare for a while just to confirm that the answer was correct. But if you take a look-see at A, and you follow its wavelength, let me change colors here so that you can actually see what I am seeing. Pen color, let's go with red. A, it starts right here, its wave, and then it goes through, and it ends right there. Okay, what other wave does that same exact pattern? Well, if you follow C, it's this dotted one right here, it does the same exact pattern. So we can say A and C have the same wavelength. Now, does A and C have the same amplitude? The answer is no, right? A is a more intense wave than C because C's amplitude only goes up to here. You can see it's relatively low compared to A, but they are what's also called in phase with each other. So when A goes up, C goes up. When A goes down, C goes down, and so forth. So that's called being in phase, which we'll talk more about later on. All right, I will see you guys next time, and hope you enjoyed the video.